So students, welcome back. We are continuing with the nuclei chapter. Nuclear density we have derived. We have done problems related to that. Mass defect done. Binding energy per nucleon. Significance of binding energy. The problems is also done. This problem also done. Binding energy curve is done. Characteristics of nuclear force is done. Now please note down this graph. Now our next topic is a graph. Distance between nucleons. Distance between nucleons in femtometer versus potential energy in MeV. We will get a graph like this, and there are certain points to be marked. This is 3 femtometer. This is 0.8 femtometer. When the distance between nucleons, what are the points to be understood from the graph? Let's see. This graph is not taken, right? This is not taken, right? Sir, this is okay. So we know that if distance between nucleons greater than 3 femtometer, force will be what? Weak repulsion. Between 0.8 femtometer and 3 femtometer, potential energy will be what? Negative. So what happened? Force will be strong attraction. Less than 0.8 femtometer distance, what happens? Potential will be large positive. So strong repulsion. So that is also done. Now let's see nuclear fission. Nuclear energy. I think we should discuss this topic. Nuclear energy. This is our next topic. The curve of binding energy per nucleon, EBN, given in figure 13.1 has a long flat middle region between mass number 30 and mass number 170. In this region, the binding energy per nucleon is nearly constant. We have seen it is equal to 8 MeV. For the light nuclear region, a mass number less than 30, and for heavy nucleus region, mass number greater than 70, binding energy per nucleon is lesser than 8 MeV, as we have noted earlier. Now, the greater the binding energy, the less is the total mass of a bound system. When the binding energy is high, mass will be less, such as nucleus. Consequently, if nuclei with less total binding energy transform to nuclei with greater binding energy, what happens? Mass will be, there will be a net energy release. That means what? Mass will be converted to energy. This is what happens when a heavy nucleus decays into 2 or more intermediate mass fragments, that is fission. Or when light nuclei fuse to form a heavy nucleus. So what happens during fission and fusion? What happens? Binding energy is increased. From where this binding energy, we get this binding energy? Because mass have been converted to energy. So please note down this system. If nuclei, from here you should note. From here you should note. If nuclei with less total binding energy transform to nuclei with greater binding energy, there will be net energy release. This is what happens when a heavy nucleus decays into what? Two more intermediate mass fragments, or that is fission, or when light nuclei fuse into form heavy nucleus. What happens? Mass have been converted to energy. In nuclear reaction, mass എന്തായിട്ട് മാറാണ്? Energy ആയിട്ട് മാറാണ്. There will be increase in binding energy in both fission and fusion. The increase in binding energy happens at the cost of decrease in mass. Remember, greater the binding energy, less is the total mass. Remember, greater the binding energy, less is the total mass of system. Binding energy കൂടുമ്പോൾ mass കുറയും. Exothermic chemical reaction. What are exothermic? Heat releasing reactions are what? Exothermic. Exothermic chemical reaction underlie the conventional energy sources such as what? Coal or petroleum. Here the energy is involved in the range of electron volt. On the other hand, in nuclear reaction, energy is in the range of what? Mega electron volt. Thus, for the same quantity of matter, nuclear source produces what? Million times more energy than chemical reaction. For example, 1 kilogram uranium generates 10 raised to 14 joule. But 1 kilogram coal generates how much joule? 10 raised to 7 joule. So, 1 kilogram of uranium generates million time. 1 million is equal to 10 lakh. Remember, 1 million is equal to what? 10 lakh. So 1 kilogram burning, 1 kilogram uranium, when 1 kilogram uranium is burned, it creates million times more energy than 1 kilogram of coal. 1 kilogram of uranium generates million times more energy than 1 kilogram of coal. See, I am directly taking from NCERT. Please note it down. I hope you are noting it down. We are discussing nuclei chapter and we are discussing how strong is nuclear energy, how enormous energy we are getting from nuclear reactions. Note it down. Note it down. Finish? Finish, right? Those who have not finished, please finish fast. Done. So let's continue. Next is nuclear fission. See, nuclear fission. New possibilities emerge when we go beyond natural radioactive decays and study nuclear reaction by bombarding nuclei with other nuclear particles such as proton, neutron, alpha particle. So what happens in nuclear fission? We bombard a nuclei with the proton, neutron, alpha particle. Out of these proton, neutron, alpha particle, more preferred choice is neutron. Why? Because uranium nuclei contain proton. And if I use a proton to start a nuclear reaction, there will be proton-proton Coulombic repulsion. So I have to spend extra energy to overcome this Coulombic repulsion. But what is the advantage of using neutron? Neutron is neutral, so there is no repulsion, so we can easily conduct the reaction. A most important neutron-induced nuclear reaction is fission. A most important neutron-induced reaction is fission. An example of fission is when a uranium isotope 92U235 bombarded with a neutron makes into two intermediate mass nuclear fragments. This is neutron plus 92U235. Initially it becomes 92U236. Then it becomes 56Ba144. Then it becomes 36 krypton 89. Then what? 3 neutron. So there was one uranium atom 92U235. When it hit by one neutron, what happens? It releases what? 3 neutrons. So that is the reason why you are seeing what? That is the reason why you are seeing 3, 0 and 1. These 3 neutrons will induce reaction on 3 different uranium atoms. So from 1 neutron induced reaction, we are releasing 3 neutrons. Those 3 neutrons will again induce reaction on 3 different uranium atoms. So from 1 to 3, 3 to 9, 9 to 27, 27 to 81, 81 to 343. It goes on like that. The same reaction can produce other pairs of intermediate mass fragments. 0 and 1 plus 92U235 implies 92U236. Then sometimes it changes to another element. It may release 4 neutrons. Then there is another example, xenon. Then what? 2 neutron. So out of these 3 reactions, any reactions are possible. That we cannot guarantee which is going to happen. The fragment products are radioactive nuclei. They emit what? Beta particles in succession to stable end product. The results are also what? Radioactive. From those radioactive elements, there will be emission of beta particles until it attains stability. The energy released is called Q value. Remember, energy released in nuclear reaction is called what? Q value. In the fission reaction of nuclei like uranium is of the order of 200 MeV per fissioning nucleus. Please understand, note this point. How much energy is released? 200 MeV per fissioning nucleus. How much energy is released? 200 MeV per fissioning nucleus. Note here, the equation note here. Equation note here. This process is called what? Chain reaction. What is chain reaction? From 1 neutron to 3, then 3 to 9, 9 to 27, 27 to 81, 81 to 343. It goes on like that. This process is called what? Chain reaction. This process in the pair is chain reaction. Abhijit was asking how to make first neutron. That will be doing, we will be taking first neutron from other reactions which is not mentioned in our textbook. How we are getting first neutron is not explained in our first textbook. That is beyond the scope of our syllabus. That is done in nuclear reaction, but how it is done, it's not in our syllabus. It will be done from other chemical reactions. Note it. നോട്ട് ചെയ്താ ആ ഇക്വേഷൻസ് നോട്ട് ചെയ്യണേ. How much energy is released per fissioning nucleus? 200 MeV. 200 MeV energy is released per fissioning nucleus. നോട്ട് ചെയ്താ now we will do one problem. Let us take a nucleus with a mass number 240, breaking into mass number 120 each. Then binding energy per nucleon for 240 nucleus will be what? How to find out binding energy per nucleon? Binding energy. What is the binding energy per nucleon? It is what? Mass number is what? 240. Mass number is what? 240 into what? If you do that, how much binding energy will be what? 7.6 MeV. Binding energy of two 120 fragment nuclei is what? About 8.5 MeV. Now, what is this binding energy? See, what is the nucleus? Let us say with mass number 240. Mass number is what? 240. So, how we are calculating this? Because I have shown this problem here. That you can check here. See, a heavy nucleus P of mass number 240 and binding energy 7.6 MeV per nucleon splits into two light nuclei Q and R. Not this one. Okay, let us continue with that problem. Okay. So binding energy for 240 is 7.6, binding energy for 120 is given 8.5 MeV. These two binding energies are given as what? First one is what? 7.6 and the other one is what? 8.5. So what is the gaining binding energy? 0.9. Why I say gain in binding energy? Because I know the purpose of nuclear reaction is to get stability and to increase binding energy. So what was the original binding energy? 7.6 of mass number 240. Now binding energy for the two 120 nucleus is what? 8.5. So what is the gain in binding energy of one nucleon? 0.9 MeV. Since mass number is 240, what is the total gain? For one nucleon, there is a gain of 0.9 MeV. So for all the 240 nucleon, what is the gain in binding energy? 240 into 0.9 or 216 MeV. This is the gain in binding energy. The disintegration energy fission events first appears as the kinetic energy. First അത് appear ആയതുകൊണ്ട് എന്തായിട്ട് kinetic energy ആയിട്ട് neutron and kinetic energy of fragments and neutrons. Eventually it is transferred to surrounding matter as what? Heat. The source of energy in nuclear reactors which produce electricity is nuclear fission. The enormous energy released in atom bomb comes from uncontrolled chain reaction. Uncontrolled nuclear fission. What is the source of energy in atom bomb? Uncontrolled nuclear fission. Nuclear reactor controlled fission. And in this example, please note down this example. It's a very important example. In this example, originally there was a mass number 240 nuclei. It splits into what? Two 120 nuclei split out. So first of all, we found out the gain in binding energy of one nucleon, which is what? 0.9 MeV. But in the mass number 240, it has 240 nucleons. So what is the total gain in binding energy? 240 into 0.9, that is 216 MeV. Any doubt? മക്കളെ മനസ്സിലായോ? പർപ്പസ് ഓഫ് ന്യൂക്ലിയർ റിയാക്ഷൻ എന്താ? ഗെയിൻ ഇൻ ബൈൻഡിങ് എനർജി, ഇൻക്രീസ് സ്റ്റെബിലിറ്റി ആണ്. ഡൗട്ട് ഉണ്ടോ? ഇത് മനസ്സിലായോ? നോട്ട് ചെയ്യട്ടോ. നോട്ട് ചെയ്തോ. നെക്സ്റ്റ്, nuclear fusion energy generation star. What happens in fusion when two light nuclei fuses to form a large nucleus, energy is released. Since the larger nucleus is more tightly bound, as seen from the binding energy curve in figure 13.1, we know that some examples of such energy liberating nuclear fusion reactions are. ഈ എക്സാമ്പിൾസ് നിങ്ങൾ നോട്ട് ചെയ്യണം, ബിക്കോസ് ഇറ്റ്സ് NCERT textbook example. In the first reaction, two protons combine to form a deuteron. Protons are combined to form deuteron, and a positron. This is positron. This is neutrino. This is neutrino with a release of energy what 0.42 MeV. Please note down this reaction. In nuclear fusion, lighter nuclei combine to form heavy nucleus. Now we are discussing nuclear fusion. Note ചെയ്തോ. We are discussing about nuclear fusion where light nuclei combine to form heavy nucleus. E plus stands for positron. Nu stands for neutrino. The opposite to that is what? Antineutrino. This is called antineutrino. Done? All of you done? So next, continuing. Neutrons combine to form light isotopes of helium. In reaction 13.13C, two neutrons combine to form a triton and a proton. For fusion to take place, the two nuclei must come. Okay, this was about the reaction. From here onwards, please note down. For fusion to take place, the two nuclei must come close enough so that the attractive short-range nuclear force is able to affect them. See, to make nuclear fusion possible, two neutrons should come closer. Not neutrons, two nuclei must come close enough so that attractive short-range nuclear force is able to affect them. However, since they are both positively charged particles, because both the nuclei contains what? Protons. Neutrons are neutral. As they come closer, there will be Coulombic repulsion. They experience what? Coulombic repulsion. They, therefore, must have enough energy to overcome this Coulombic barrier. The height of the barrier depends on the charges and the radii of the interacting nuclei. It can be shown, for example, the barrier height of two protons is around 400 keV. What is the barrier height of two protons? 400 kilo electron volt, and is higher for nuclei with the higher charges. We can estimate the temperature at which two protons in a proton gas would averagely have enough energy to overcome the Coulombic barrier. How it is calculated? We know that 3 by 2 kBT, this is average kinetic energy, should be equal to what? The barrier potential of protons. What is the barrier height? 400 keV. What is Kb? Boltzmann constant. So 3 by 2 into 1.38 into, what is Boltzmann constant? Into 10 raised to minus 23 into T is equal to what? 400 into 10 raised to 3 eV. If you substitute, T will be what? Around 3 into 10 raised to 9 Kelvin. What is the temperature requirement? 3 into 10 raised to 9 Kelvin. So how much temperature is required for the fusion to take place? Very high temperature. So 3 by 2 kBT, Kb is Boltzmann constant, is equal to 400 kVe, which is equal to what? 3 into 10 raised to 9 Kelvin. When fusion is achieved by raising the temperature of the system so that particles have enough kinetic energy to overcome the Coulombic repulsive behavior, it is called thermonuclear fusion, which is a very important question. Why fusion is called thermonuclear fusion? Because when two nucleus come closer, there will be Coulombic repulsion. So we have to put extra energy. These particles should have large kinetic energy to overcome that Coulombic repulsion. For example, the energy required for the fusing of two protons is what? 400 keV. So what should be the temperature required? How I am calculating that? 3 by 2 kBT is equal to what? 400 kilo electron volt. And I am substituting for T, temperature. And my answer is what? 3 into 10 raised to 9 Kelvin, which is a huge temperature. So fusion occurs at what? Only at a very high temperature. This paragraph, these lines are very important, including this calculation for your board and also entrance. ഈ ബ്ലൂ ലൈനിലെ ഈ സെക്ഷൻ നോട്ട് ചെയ്യണം. ദിസ് ഈസ് ഇമ്പോർട്ടൻറ്റ് ഫോർ യുവർ എൻട്രൻസ് ആൻഡ് ഓൾസോ ഫോർ ബോർഡ് എക്സാം. So this proves that fusion occurs only at a very high temperature. അത് മനസ്സിലായോ? മാഷ് പറഞ്ഞത് മനസ്സിലായോ? മനസ്സിലായോ സാറേ? നോട്ട് ചെയ്യട്ടാ. So through these two paragraphs, we are trying to say that it's not easy to conduct nuclear fusion because fusion happens only at an extremely high temperature. So that is the reason why we call it thermonuclear fusion. കഴിഞ്ഞോ? നോട്ട് ചെയ്തെല്ലാവരും? So we are directly studying from NCERT. For NEET also, this is more than enough. NEET ആണെങ്കിലും ചെയ്യുകയാണെങ്കിലും ഇത്രയ്ക്ക് തന്നെ ഇന്ന് വരുള്ളൂ. So let's continue. Thermonuclear fusion is the source of energy output in the interior of star. The interior of the sun has a temperature of what? 1.5 into 10 raised to 7 Kelvin, which is considerably less than the estimated temperature required for the fusion of particles of average energy. Clearly, so directly fusion is not possible. Clearly, fusion in the sun involves protons whose energies are much above the average energy. So proton energy is what? Much higher on, because there is not enough temperature. There is not enough temperature because it's only what 1.5 into 10 raised to 7 Kelvin, and we have seen what is the temperature required, 3 into 10 raised to 9 Kelvin. So still how fusion is possible? Because protons in sun is having what? High energy. Okay. The fusion reaction in the sun is a multi-step process. Generally, these multi-step processes are two cycles are there. PP cycle. First one, PP cycle, which stands for proton-proton cycle. Proton-proton cycle. And the second, what happens in proton-proton cycle? Hydrogen atoms combine to form helium. Next cycle is carbon cycle. What happens in carbon cycle? When hydrogen in the core of the sun gets completely depleted, carbon cycle starts. Deplete ചെയ്യാ പറഞ്ഞാൽ അവസാനിക്കുക, കഴിയുമ്പോൾ carbon cycle starts. What happens in carbon cycle? I am writing with a red pen. In carbon cycle, helium combine to form carbon. In carbon cycle, what happens? Helium combine to form carbon. That is the specialty of carbon cycle. Helium combine to form carbon. That is the specialty of carbon cycle. So what are the two cycles in sun? PP cycle, proton-proton cycle, and the next one is what? Carbon cycle. What is the specialty of proton-proton cycle? Hydrogen atom combine to form helium. The fusion reaction in the sun is a multi-step process in which hydrogen is burnt into helium. Thus, the fuel in the sun is hydrogen in its core. The proton-proton cycle by which this occurs is represented by the following four set of reactions. Now remember, for the fourth reaction to occur, first three reactions should occur two times. For the fourth reaction to occur, the first three reactions must occur 2 times. In which case, 2 light helium nuclei unite to form ordinary helium nuclei. 2 light helium nuclei unite to form ordinary helium nuclei. And what is the other cycle? Carbon cycle. What is a carbon cycle? Helium, when the sun in the core hydrogen complete കഴിയുമ്പോൾ carbon cycle start ചെയ്യും. What happens in carbon cycle? Helium combine to form carbon. Carbon എന്ന് പറഞ്ഞാൽ കരിയാണ്. അങ്ങനെ കരി ഉണ്ടാവും എന്ന് പറഞ്ഞാൽ അതിന്റെ അർത്ഥം എന്ന് വെച്ചാൽ സണ്ണിന്റെ കത്തിക്കൽ കഴിഞ്ഞു. നമ്മൾ പറയില്ലേ അതിന്റെ കത്തിക്കൽ കഴിഞ്ഞു എന്ന്. അതുപോലെയാണ് ഈ കാർബൺ ഉണ്ടാവും എന്ന് പറഞ്ഞാൽ. പോയിന്റ്സ് നോട്ട് ചെയ്യട്ടാ. ഹലോ, രണ്ട് സൈക്കിൾ ഏതൊക്കെയാ? PP സൈക്കിളും കാർബൺ സൈക്കിളും. PP സൈക്കിൾ പ്രോട്ടോൺ പ്രോട്ടോൺ സൈക്കിൾ, കാർബൺ സൈക്കിൾ ഹീലിയം ആറ്റം കമ്പൈൻ ടു ഫോം കാർബൺ, PP സൈക്കിൾ ഹൈഡ്രജൻ കമ്പൈൻ ടു ഫോം ഹീലിയം. Can you explain the second reaction? Positron plus electron gives gamma radiation. This stands for gamma. But actually there are three types of radiation: alpha, beta, gamma. But that is deleted from the syllabus. So it will be confusing for you. Okay, since you are asked doubt, I can explain. But actually it got deleted from the syllabus. So let's see. See, suppose there is an element X set A, and when this element releases alpha particles, it becomes Y, its atomic number decreases by 2, mass number reduces by 4, and then a helium nucleus comes out plus energy. This is alpha decay. Now beta decay, it is of two types. Beta decay, beta negative decay, beta positive decay. In beta negative decay, beta negative particle, electron, beta negative particle is electron, beta positive particle is positron. So what happens in beta decay? There are two types of beta decay. Suppose there is an element X set A, and after beta negative decay, it becomes Y, atomic number increases by 1, no change in mass number, plus energy. Similarly, beta positive decay, X set A, after beta positive decay, what happens? Atomic number decreases by 1, and it becomes another element, and there is no change in mass number. In either of the beta decay, there is no change in mass number. Now, I can explain further. In beta decay, a neutron decays into beta negative decay, proton, electron, and antineutrino. In beta positive decay, a proton decays into neutron, positron, and neutrino. This is what? Positron. This is what? Neutrino, antineutrino. This is what? Neutrino. So some might be wondering, what is neutrino? Massless particle. Massless, does not, no interaction with the matter. This is what? Antineutrino. And this one is what? Electron. So what happens in beta negative decay? In beta negative decay, what happens? Mass number increases, no change in mass number, atomic number increases by 1. Why atomic number increases? Because one proton is evolved. What is the atomic number? Number of protons. See, after the reaction, what happens? One extra proton comes. So that is the reason why atomic number increases by 1 in beta negative decay. So what is the problem with the beta positive decay? Now why there is no change in mass number here? One neutron goes and another one proton comes. So mass number remains the same. In beta positive decay, what happens? Proton converted to neutron. What is said? Atomic number is number of protons. So we are losing one proton and one neutron we are getting. So proton lost means what? Atomic number decreases by 1. Z minus 1. It should be Z minus 1. Atomic number minus 1. So atomic number is decreasing by 1. Any doubt? Yeah. So I am coming to the gamma decay. After alpha decay and beta decay, nucleus will be in the excited state. Then it comes back to ground state. Then it comes back to ground state. Ground state. After emitting one or more gamma rays. Gamma ray. Gamma XZA. After gamma, this is the symbol gamma, it becomes XZA only. There is no change in atomic number and mass number. Gamma is energy only. Energy only. So no change in mass number or atomic number. Mass number ZA or atomic number Z. Because gamma is what? Energy only. So after alpha and beta decay, nucleus will be excited state. It comes back to ground state by emitting gamma radiation. See, many teachers will say alpha particle, beta particle, gamma particle. No, gamma is not a particle. Gamma is a radiation. So that is the reason why even after gamma coming out, there is no change in mass number or atomic number. It's just an energy. Positive beta decay energy in the, yes. Energies, yeah, which I forgot to, in all nuclear reaction there will be energy, not only positive decay. In gamma also there is energy. I forgot to write that. There is energy. There will be energy release. ഇത് പക്ഷേ ഡിലീറ്റഡ് ആണ്, ബോർഡ് എക്സാമിന് ഇല്ല. CBSEക്കൊക്കെ ഇത് ഡിലീറ്റ് ചെയ്തു. എൻട്രൻസിന് നീറ്റിന് ഇല്ലാന്ന് തോന്നുന്നു, എനിക്ക് ഡൗട്ട് ഉണ്ടോ ഇല്ലെന്ന്. നോട്ട് ചെയ്തു, എന്തായാലും എടുത്താലേ നോട്ട് ചെയ്തു. നോട്ട് ചെയ്യട്ടോ. Note ചെയ്താ? Done? Finished? So coming back to our original question. I hope you have done this. If not finished, please finish fast. അയ്യോ കാണുന്നില്ല ഇവിടെ. No, I think tomorrow I will be finishing this chapter. Nucleus chapter will be finished tomorrow. So we'll be doing all the problems from Nucleus chapter. I hope you have done. Now what happens here? This is the conclusion. 4 hydrogen atom combine to form helium atom with the release of how much energy? 26.7 MeV. In this nuclear reaction, what happens? 4 hydrogen atom combine to form helium with the release of how much energy? 26.7 MeV. Now, helium is not the only element that can be synthesized in the interior of a star. As the hydrogen in the core gets depleted and becomes helium, the core starts to cool. The star begins to collapse under its own gravity, which increases the temperature of the core. So what happens? Due to its own gravity, star begins to collapse. This will increase the temperature. If this temperature increases to about 10 raised to 8 Kelvin, we know that again fusion will take place. Fusion takes place again. This time of helium nuclei into what? Carbon. This is called what? Carbon cycle. This kind of process can generate through fusion higher and higher mass number elements. But elements more massive than those near the peak of the energy curve figure cannot. Okay, that is not required. Up to this point, you should note down. What happens? What happens? When the hydrogen in the core gets completely depleted, what happens? Temperature, the star begins to fall under its own gravity. That makes the temperature high. At this high temperature, what happens? Helium combines to form what? Carbon. Because the temperature will be around 10 raised to 8 Kelvin. So again fusion takes place. In this fusion, helium combines to form carbon. How much energy is released per nuclear fusion of nuclei? 26.7 MeV. When 4 hydrogen atoms combine to form one helium, how much energy is released? 26.7 MeV. Note data, note. Now let's continue. The age of the sun is about 5 into 10 raised to 9 years. It is estimated that there is enough hydrogen in the sun to keep it going for another 5 billion years, so we don't have to worry. After that, the hydrogen burning will stop and the sun will begin to cool and will start to collapse under gravity, which will raise the core temperature. The outer envelope of the sun will expand, turning into called red giant, which is the end stage of a star. So what happens at the end? What happens? Sun becomes a red giant and it will die, but it will happen only after 5 billion years. So we don't have to worry. Now, controlled thermonuclear fusion. The natural thermonuclear fusion process in a star, which occurs naturally, is replicated, or the same method is copied in thermonuclear fusion device. Why thermonuclear fusion? Because fusion requires high temperature to overcome the Coulombic repulsive force. In controlled fusion reactors, the aim is to generate steady power by heating nuclear fuel to temperature in the range of 10 raised to 8 Kelvin. Why that much temperature is required? Because we have to overcome the proton-proton repulsion. At this temperature, the fuel is a mixture of positive and negative ions, which state is called what? Plasma. The challenge is to confine this plasma. It's not easy to confine this plasma. There should be a vessel to contain or handle this 10 raised to 8 Kelvin. Since no container can stand such a high temperature, the challenge is to confine this plasma because no container can stand such a high temperature. Several countries around the world, including India, are developing techniques in this connection. If successful, fusion reactors will hopefully supply almost unlimited power to humanity. If fusion reactors are possible, then we don't have to worry about the power because enormous energy can be generated from fusion reactors. So the energy possibility from nuclear reactors, fusion reactor is enormous. So end stage of a star is called red giant. That also should be noted. So sun എത്ര കാലം കൂടി കത്തിക്കും ഇങ്ങനെ കത്തി നിൽക്കും 5 billion years. That's a very huge amount of time. So we don't have to worry about our extinction because sun will be there. Okay, next class we will be doing problems only. So we have finished nuclear chapter theory set. We have done little bit of problems also. Next class, tomorrow's class will be full of problems. So thank you students, good night. Thank you.